Hello and welcome. Today we're going to be talking about estimation of series of values using error analysis. So the idea here is that we have a series, we'll call it S, and it's equal to the sum starting from n equals 1, or it could be any number really, all the way up to forever. Okay, and we have some an there. Okay, and I want to know what that value is, given we know what an is. Okay, so there are two strategies. For two types of series. And we're going to talk about those two types. We're going to talk about alternating series. And we're also going to talk about series involving series that converge via the integral test. Okay, so a few notes here. All right, so these are the two categories we're going to talk about today. We have a few things we're going to talk about here. One thing, we're not going to talk about. We're not talking about Taylor series here, or any power series. Okay, so we're not talking about functions of x here, all right? So you're going to have to see a different video, see other videos. See other videos for that. And the other thing we're going to make sure to note here is that S, our series in question, we can assume or require that the series that S is convergent. Okay, so we're not going to check convergence in this particular video. We're just going to assume convergence, or at least check it really briefly. We'll assume that we already know we're dealing with a series that does have a finite value. Obviously, the testing process for determining if a series converges or not is an important question to answer. First, we'll assume that we've already done that in this video. Okay, and again, we're not talking about Taylor series here. We're only talking about these two series right here, alternating series and series that we can deal with the integral test here. Okay, so let's now talk about the two different tests. So I'm going to talk about the alternating series test. Series estimation. Okay, as in any, well, actually, with any test, so the idea is we have this. We have Sn, which is equal to the sum. N starts at 1, but goes only up to capital N there. All right, and we have a -1 to the n times Bn. Right, and this is an alternating series, and the Bn's, of course, are positive numbers, and the limit as n goes bigger of the Bn goes to 0. Okay, and this is, of course, just the requirement for our series to be alternating. And the question we have is, how far away is Sn from S itself? So I'm going to actually I'll call that the error. All right, and it turns on it has an answer. So the theorem, and it's a very simple theorem, states that Sn minus S is less than or equal to B capital N plus 1. And that is a very easy test to remember. All right, so let's go from there. All right, so I also want to talk about, so right there, that right there is our alternating series test. Right, so I want to talk about one more. I'll talk about the, well, I'll do it on a separate page here. I'm going to talk about the integral test. Estimation. Okay, and this test involves a different type of series. So here we're going to have s is equal to the sum. N starts at 1 or some other index. We have a of n like that. And I want to look at a truncated series, a series that's a finite sum that goes up to capital N of a n. Okay, and the first thing, the first hypothesis we have, of course, is that a n is positive, and that the limit n goes to infinity of a n goes to 0, and that we have f of n is equal to a of n. So for f of x is some function, we can integrate. All right, so those are the assumptions we have on this. And this test, what we so the theorem is then we want to know, again, the question is, we want to know how big is this error. And then so the question then is how big. So this particular theorem, I'm not going to prove it, but it's a really basic theorem. It's not quite as simple as the alternating series estimation, but it goes like this. We can bound above and below by taking the integral of f of x from n to infinity, and that bounds my error above, and then we can also bound it below by n plus 1. So this theorem gives you more than information just how big it is. It also tells you how small it is, in a sense. Okay, that tells you that both an lower and an upper bound on how the size. So you can get a really good estimate of these things. All right, so those are the two theorems. Now let's go practice these. Let's do the first one. Let's do it on this page here. We're going to use this theorem on an integral test appropriate series. All right, so the question I have then is I'm going to say that I'm going to start with n is equal to 10. Okay, and my question is S10 of the following series, n equals 0 all the way to into infinity. Oops, not infinity, my bad. We're just going to 10, right? Okay, and I have 1 over n squared plus 1. All right, so I want to know, how big is S10 and how close is it to the original series? And the series I'm interested in, of course, is the sum starting from n is equal to 0, going all the way up to forever of 1 over n squared plus 1. All right, so I want to know, is S10 a good approximation? Or how good is it? So we'll use the test. So again, the test, what we have to do is look at and find out what the f of x is. And of course, the f of x is equal to 1 over x squared plus 1. Okay, and then the test, then I need to compute two things. I need to compute the, so again, n is equal to 10 here. So I'm going to integrate starting from 10 and up to infinity of 1 over x squared plus 1 dx. So this particular integrand has a nice antiderivative. It has the inverse tangent antiderivative. So we can use the fundamental theorem of calculus. From 10 going up to forever. And this has a so I'm going to do this carefully by writing that out there, minus inverse tangent at 10. This has a nice calculation. So this right here, that's actually equal to pi over 2. So this is going to be pi over 2 minus tangent inverse of 10. This particular value, I actually calculated ahead of time. It's 0.0997. Okay, cool. All right, so the next thing I want to do is calculate the other integral. So now we're going to go, it said it was n plus 1, so that's going to be 11 to infinity, 1 over x squared plus 1. So this is the lower bound, so we expect this to be a slightly smaller number. And of course, that's going to be pi over 2. It's the same calculation as before, except we're going to replace 10 with 11. Tangent inverse of 11 right there. Okay, let's check what this is. So I pre-computed this ahead of time. It's going to be 0.0907, so just slightly smaller. All right, so there we go. Those are our two numbers. So we can use the theorem. To say that 0.0997 is the lower bound for the error. And the upper bound is 0.09. Oops, I made a mistake here. My bad. I got my bounds turned around here. That is 0.7. This is 997. All right, so that's our bounds for our error. So this would answer a question, for instance, is s to the x10 within 1/10? And the answer, of course, is yes, because we see right here that the error, it cannot be greater than 0.09, which is, of course, smaller than 0.1. So yes, that answers that question just fine. All right, so now let's turn back to the alternating series and do an example of an alternating series. Okay, so now let's talk about this specific example. I'm going to have s is equal to the sum, n equals 0 up to infinity. And the series terms will be -1 to the n all over 2 to the n. Okay, so in this case, the bn, the non-alternating component, is going to be 1 over 2 to the n. Okay. All right, so the question is as follows. What minimum capital N is needed to get s capital N minus s within 1/31st? I want to find out the answer to that. Okay, so let's use, okay, of course you're going to use the theorem. So we know that s capital N minus s, yeah, so this again is the answer. So we're going to use the theorem here. It has to be less than or equal to b capital N plus 1, which in this case is going to be 1 over 2 to the capital N plus 1. Okay, so that's using the theorem. So I want that to be less than 1 over 31. All right, so for this, then I just have to I have to find out what the n is. So let's consider a few possibilities. 2 to the 1, we know that that's 2. Okay, 2 to the 2, that's 4. 2 to the 3, that's 8. 2 to the 4, that's equal to 16. And 2 to the 5, that's equal to 32. Okay, so clearly 1 over 2 to the fifth, that's equal to 1 over 32, which is actually just less than 1 over 31. Okay? All right, so it looks like the n plus 1 has to be equal to 5. Okay? And that implies then that the capital N, the required capital N, has to be equal to 4. All right, so let's recap then. N needs to be 4 to get within that certain level of accuracy. So of course Sn, I should say S4, which is going to be equal to, let's look at it again. It's going to be this. Little n starts at 0, all over 2 to the n. What is this exactly? Let's just actually go ahead and actually compute it. This is going to be 1 minus 1/2 plus 1/4. Okay, and then minus 1/16, and then plus 1/32 there. All right, does that work out? That gives us all 5 terms, because this is the n equals 0 term, n equals 1, n equals 2, 3, and then 4. The 4th term is right there. Oh, you know what? I just made a mistake. I'm sorry, guys. I was a little confused there. I think I skipped one, and I did. There's 8, and there's 16. Okay, that's better. All right. So that whole thing is within 1/32 of, or 31st of the full series. So if I add up all of them, if I add up infinitely more, I'm only going to add a tiny bit more to the series. Only a little bit more accuracy I can get. At least it's going to be an accuracy less than 1/31. Okay. So I hope that gives you 2 examples here of how to use series estimation theorems, the 2 ones that we're going to talk about, alternating series and the integral estimation theorem. Both of them are applied to different types of series, but they can be used to estimate approximations of series. And this is, of course, very important in practice when one is using series to compute things. We can't ask a computer to add up infinitely many numbers, so we have to stop at some point. But we want to stop at a point that's reasonable, that gives us accuracy that we require for a particular application. All right, thank you very much.